Okay, welcome everyone back for the second talk of the afternoon. It's a pleasure to introduce Malik Younsi from Hawaii, who couldn't make it because of not his fault. Okay, and he's gonna talk about miracles of holomorphic motions. And go ahead, Malik.
Okay, thank you, Ront. And yeah, let me thank the organizers for this workshop. Unfortunately, I was not able to attend in person because my flights got canceled because of this Air Canada strike. They rebooked me to a later flight, which also ended up being canceled. And then by then it was too late to book anything. Everyone was trying to rebook at the same time. So um, yeah, I'm stuck here, and I'm sorry I'm not able to be with you. But hi everybody, and it's good to see you at least virtually. Um, yeah, so today I wanted to talk about something that I've been interested in for a few years now. That's holomorphic motions. So everything that I'm going to present is joint work with various people. So there's a couple of papers um, with so, for example, Tom Ransford and two of his former students, Aidan Führer and Wenwei Ai, and also my own student, Catherine Manson, who's here right now in Toronto. She knew better than to use Canadian Airlines to get to Toronto from Hawaii. Um, so yeah, the title of my talk is Miracle of Holomorphic Motions. That's actually not my title. I used a title of a very nice survey article on holomorphic motions by Kari Asala, who I believe is in this room. I think I saw him earlier. So if that's the case, then hi, and I hope you don't mind me using your title for my presentation. Um, Actually, I'm going to use more than your title. I have a quote from this nice survey paper that you wrote that I would like to start with. So what draws us to mathematics and maintains its spell upon us? A beautiful example of such phenomena are no doubt the holomorphic motions discovered by Manet, Sad, and Sullivan in the mid-1980s. So the notion can be explained in a few lines to anyone interested in mathematics and with an intrusive interpretation even beyond. So there is a deformation of the space with a non-standard concept of time. Time is assumed to vary holomorphically. Nothing more is assumed, and yet the conclusions are very strong and unexpected. One cannot avoid an everlasting astonishment. And that illustrates a lot what I think about holomorphic motions and what I hope to convey in this talk, that the definitions are very simple. There's not much in terms of assumption, but then it turns out that we can prove a lot about these holomorphic motions. And that's sort of going to be the theme throughout the presentation. Okay, so what is a holomorphic motion? So the idea is we start with a set in the sphere, so let's call it A, and then a holomorphic motion of the set A is a function of two variables. So a first variable in the unit disk, second variable in the set A, with values in the Riemann sphere, such that the following three conditions hold. So the first condition tells us that if we fix the second variable Z, which belongs to A, and we think of this as a function of the first variable lambda, then it should be holomorphic on the unit disk. And then we have another assumption about if we fix the variable lambda, the first variable, and we think of this as a function of the second variable Z, then we want this to be injective. So no other regularity assumed, just injectivity. And then lastly, it should start at the identity when lambda is equal to 0. Okay, so holomorphic in lambda, injective in Z, and it starts at the identity. Um, and one thing we can note is that there's no assumption uh, on the holomorphic motion as functions of two variables, functions of the pair lambda Z. So there's no joint continuity assumed. So just some terminology. So I'm going to, during the presentation, use F lambda to denote the maps that we obtain if we fix the parameter lambda in the disk, and we think of this as a function of Z. So the only thing we know about these functions now are that they're injective. That's from the second condition. Okay. And then I'm also going to assume that each of those maps F lambda fix the points 0, 1, and infinity, which we can always assume by composing with the Mobius transformation if necessary. Okay. Okay, so a very simple definition. So why do we care about holomorphic motions? Well, they were actually introduced by, motivated by applications to holomorphic dynamics. So there was a paper in the 1980s by Manoa and Sullivan in which they made the following observation. So they observed that Julia sets of certain rational maps often move holomorphically with holomorphic variations of the coefficients. Um, so this is quite well known, but I can just show maybe a sort of an fractal software just to illustrate this. So let me just share a different screen. Hopefully you can see. It's a little bit distorted. Let me try to fix this. Yeah, so here on the left, you have the Mandelbrot set. So if we focus on the main cardioid, as I move my mouse around, then you can see the variation of the Julia sets on the right. And they do move according to a holomorphic motion. This is a special case of this Manoa and Sullivan observation. Yeah. Okay, so let's go back to the slide. Give me a second. Share slides. Okay, so if I look at the video of the room, I think I see the slides back, so you should be able to see them as well. Okay, so this was the observation by Manoa and Sullivan. Oops. Okay, so let's just keep going with another quote. Sorry to put you on the spot, but I think it's a very nice quote. So in practical terms, so that's about the definition that we just saw for holomorphic motion. So in practical terms, we're discussing deformations with no assumptions at all on the space variable, that's the variable z, continuity or even measurability, while the key property is the holomorphic dependence required from the time parameter. That's the parameter lambda in the unit disk. As innocent as this mere last assumption may appear, let us see how far it can take us. Be ready for surprises. So what do we mean here in terms of surprises? Well, a first surprise is that we do get some information about the joint behavior of holomorphic motions as functions of the pair lambda z. So there's a theorem that was proved by Manoa and Sullivan in this paper, which is usually referred to as the lambda lemma. So it says that every holomorphic motion can be extended to a motion of the closure of the set. And moreover, the extension is always jointly continuous in the pair lambda z. Okay? And then one last quote, I promise. So the Manoa-Sullivan proof was so simple and the results so unexpected that upon seeing the argument, each of us complex analysts stood in bewilderment. How is this possible? Okay, so now after this lambda lemma was proved, so we know we can extend holomorphic motion to the closure of the set. And there was a conjecture a couple of years later by Sullivan and Thurston, where they conjecture that every holomorphic motion of any set whatsoever should be extendable to a holomorphic motion of the whole Riemann sphere. So that was conjectured in 1986, and it was actually proved a couple of years later by Slodkovsky um, in a remarkable paper using techniques of several complex variables. So Slodkovsky showed that indeed, if you start with any holomorphic motion, you can always extend it to a holomorphic motion of the whole Riemann sphere. Okay, so this shows that we can focus our attention on motions of the whole sphere that are defined on the whole Riemann sphere. And this is what I'm going to do throughout the presentation. Okay, so all the holomorphic motions that I'm going to talk about, they're assumed to be defined on the whole Riemann sphere. And if that's the case, if we have such a motion, then we can look at these maps, F lambda, that we discussed. So those are the maps. Remember that if you fix the parameter lambda and you think of this as a function of z, so by definition, they're only assumed to be injective, but because of the lambda lemma, we know that they're actually homomorphisms. And the question is, what is the precise degree of regularity for those homomorphisms? Can we get something a little bit better? And as most of you probably know, the answer is well known. Those homomorphisms, they turn out to be quasi-conformal mappings. So I think here I have a slide about the definition of quasi-conform mappings. It's not really needed in this workshop, but just in case. Um, so the homomorphisms, they satisfy this Beltrami equation for some Beltrami coefficient, which is a measurable function. Here I'm only considering quasi-conform mappings on the whole sphere. So we get a Beltrami coefficient defined everywhere with L infinity norm less than 1. Um, and then also some terminology that will come back later. When I write little k quasi-conformal, I mean that the norm of the Beltrami coefficient is at most little k, which is assumed to be strictly less than 1 by quasi-conformality. Okay? Okay, so what's the connection between those quasi-conform mappings and holomorphic motions? Well, one way to summarize the connection is to state it in the following way. So that's usually referred to as the extended lambda lemma, which says that the following are equivalent. So being a holomorphic motion is equivalent to the fact that for each lambda in the disk, the maps f lambda have to be quasi-conformal, and the little k can be taken to be the absolute value of the parameter lambda. And we also have some holomorphic dependence of the Beltrami coefficients on this parameter lambda. And that's an if and only if you have sort of a collection of quasi-conform mappings which depend holomorphically on lambda, then that gives you a holomorphic motion. So as I just said, there's this very deep connection between holomorphic motions on one hand, and then families of quasi-conform mappings which depend holomorphically on the parameter lambda. And not only that, but if we start with an arbitrary quasi-conform mapping, we can always put it inside a holomorphic motion. There's sort of a canonical way to do this. So that means that if you want to study properties of quasi-conform mappings, then you can put them inside holomorphic motions and try to prove things about holomorphic motions instead. And that turned out to be a very fruitful approach over the years. So I have a couple of applications that I can mention. First of all, I noticed that Loevner theory was part of the description of this workshop, so I thought I could mention some applications of holomorphic motions to the Loevner equation. So I found a few papers where they studied quasi-conformal extendability of maps on the unit disk using holomorphic motions. And also they studied quasi-conformal extendability of Loevner chains. So there's been some work done on this topic using holomorphic motions to study properties of conformal maps and quasi-conformal mappings and Loevner chains. And then something that I've been looking at lately is the Loevner equation driven by complex valued functions. There's a nice preprint by Tran where he studied the Loevner equation. So you have the deterministic Loevner equation here. But instead of looking at Loevner equation generated by a real value driving function, what you do is you take as driving function a complex valued function of the form some complex number alpha in the unit disk multiplied by some suitable function. It should be holder 1/2 so that the solution will be generated by a simple curve. And so what you do for each alpha, you can solve. This is what Tran does: is he solves the Loevner equation, so you get a curve for each parameter alpha, and these curves actually come from a holomorphic motion. This is proved in that paper. So when you solve this equation for this choice of the driving function, then you get a holomorphic motion of a line segment. And something that I wonder, I don't know the answer, but can you do the same thing for Brownian motion? So instead of taking a 1/2 holder continuous function, you try to redo the same analysis, but you replace this W by some complex number multiplied by Brownian motion. I don't know if you can solve the stochastic Loevner equation in this case, and maybe you get holomorphic motion or some kind of random version of some kind of random holomorphic motion out of this. It's sort of, the idea would be sort of to study SLE, but with complex values for the parameter kappa. Okay. So I don't know if it's been done. I think that's an interesting question. And in a different direction, there's also been a lot of work on proving properties of quasi-conform mappings using holomorphic motion. And there's a seminal paper on the subject by Asala, once again, where he showed optimal distortion bounds for the variation of dimension under quasi-conformal mappings. So we have these inequalities, which are pretty famous, for the image, the dimension of the image of a set under a quasi-conformal mapping. And the bounds depend on the little k or the capital K for the quasi-conformal map. So this uses holomorphic motions in a fundamental way. And also another ingredient in the proof is the study of the optimal sublet regularity of holomorphic motions. Equivalently, the higher order integrability of the Jacobian of quasi-conformal mappings. So this will come back later in the talk. And then there is also a follow-up paper to this one by Smirnov, which is also very famous on the dimension of quasi-circles. So the idea is that if you look at these bounds that Asala obtained, and if you take A to be the real line, then the dimension is 1. So on the right-hand side, you're going to get 1 minus 1/2, so 1/2. And then on the left-hand side, you're also going to get a 1/2 times 1 over capital K. And then if you just manipulate these inequalities a little bit, that gives you an upper bound for the dimension of the image of the real line under a little k quasi-conformal mapping, which is called a little k quasi-circle. And the bound that you get, the upper bound from these inequalities, is 1 plus k. And this was conjectured that you can actually improve this to 1 plus k squared, which was proved by Smirnov a few years later in 2010. So now we know that the dimension, the Hausdorff dimension of a k quasi-circle is at most 1 plus k squared. And this was proven to be not sharp. It's not a sharp inequality by Oleg Ivry in 2015. Okay, so a couple of applications of holomorphic motions, namely mostly to the study of properties of quasi-conform mappings. And I think of these theorems as special cases of a more general question. So that's sort of the question that I'd like to discuss today. And that's the following. So suppose you start with a set valued function. So just a real valued function defined on subsets of the plane. And then you start with a set A in the plane and you consider a holomorphic motion of the whole sphere. So what you can do is you can move the set A around using the holomorphic motion. So you apply these maps F lambda to the set A. And then you can try to see how the set function changes when you do this. So in other words, how does this function here vary depending on the parameter lambda? What is the behavior of this function? And this is a general question that has been studied a lot in the literature for different choices of the set valued function. So you can either consider different choices of the set valued function, or you can fix the set valued function, and then you can look at different types of set A and then study this function. For example, if A is the Julia set of a, I don't know, hyperbolic rational map in dynamics, so this was, and if F is Hausdorff dimension, then this was studied by Ruel in this seminal paper, which was sort of the landmark of thermodynamic formalism. So looking at the variation of the Hausdorff dimension of Julia sets of hyperbolic rational maps, there's also a paper by Tom Ransford where he studied this as well. And there's a lot of work that has been done on this subject. So I mentioned a lot of papers. I can't discuss each of them, but they're all quite interesting, and they look at this question from different perspectives. So either different set value function or different types of set A. Okay. So here, Asselas and Smeister, I think this is the variation of dimension of limit sets of Fuchsian groups. Eremenko-Hamilton is about this question when F is the area measure, two-dimensional Hausdorff measure, and there's a variety of results related to this general question. Okay, and I sort of try to, it's hard to make an exhaustive list, but I try to summarize a couple of these results in the following table. So here on the left, you have different possibilities for the set function. For example, we have S-dimensional Hausdorff measure as the first entry. Then there's area measure, Hausdorff dimension, packing dimension, or Minkowski dimension, so just various notions of dimension. We can study how these dimensions changes under holomorphic motions. And there's also in the table some notions of capacities as well. So logarithmic capacity, condenser, analytic, continuous analytic capacity. And then in the middle column here, I indicated whether the variation of this specific set function under holomorphic motion is continuous. So in other words, if we go back to this function in the question, for the specific choice of f, is this function a continuous function on the unit disk? So we see that in a lot of cases, the answer is yes, and in some cases, the answer is no. And if the answer is yes, what more can we say about the function? Can we sort of describe the optimal regularity that we can get for an arbitrary set A? So the results of this table is for an arbitrary set A. So for example, area measure, we know it varies continuously. This is not difficult to prove, but then I don't know the precise regularity. Same thing for some notions of capacity that vary continuously, but the regularity is not known. I have a student, Catherine, who's working on these types of questions. And what I want to talk about today is more related to variation of dimension. So we have these three dimensions that we studied, Hausdorff dimension, packing dimension, Minkowski dimension. It's easy to see that they vary continuously. This is not difficult. But then what about the optimal regularity? Can we sort of characterize the variation of dimension under holomorphic motions? And we do know the answer for packing dimension, so we have a complete characterization. For Hausdorff and Minkowski, unfortunately, we don't know quite the answer, but we're almost there. So we have some partial results that I'd like to mention today. Okay. Any question so far? Okay, so like I said, I'd like to talk about these dimensions under holomorphic motions. But it turns out that it's a little bit easier to study logarithmic capacity, for example. So let's start with this as sort of a toy case to try to explain the kind of answers that we obtain. So let's look at the variation of logarithmic capacity under holomorphic motion. And for this, it turns out that the definition of logarithmic capacity that's more convenient to use is the definition in terms of the transfinite diameter. So this is defined in the following way. We consider this sequence called the nth diameter corresponding to a given compact set E, where what we do is we try to maximize the product of pairwise distances among all n tuples of points in the set E. And then there's some kind of normalizing exponent here. And then it turns out that this is a decreasing sequence. So it has a limit, and the limit is called the transfinite diameter. It turns out to be equal to the logarithmic capacity of the set E. Okay? So let's try to keep this definition in mind and then try to study how logarithmic capacity changes under a holomorphic motion. So in the table, I indicated that it changes continuously, and that's actually a theorem that we have here. We proved a couple of years ago. So if we have any compact set and any holomorphic motion, then the logarithmic capacity changes continuously. It's a continuous function of the parameter lambda. And the idea of the proof is the following. So first of all, let's consider n distinct points in the set A. So let's assume that it's infinite without loss of generality. And then the first observation is that if you look at the log of the absolute value of this product that you have here, and you think of this as a function of lambda, then this is going to be a harmonic function on the unit disk. And the reason is the following. So here the zj and the zk are fixed. So what you're doing is you're applying those maps f lambda, which are holomorphic in the parameter lambda. So what you have here inside the absolute value is the product of holomorphic functions. So this is definitely a holomorphic function itself. It's also a non-vanishing holomorphic function because of the injectivity assumption that we have about the holomorphic motions. So what we do have here is the log of the modulus of a non-vanishing holomorphic function, and we know that this is always a harmonic function. Okay. And now using this observation and using the definition of the end diameter, it follows from this that if you take the log of the end diameter of f lambda of the set A, so you move around the set A using a holomorphic motion, and you look at the end diameter, and you take the log of this, because the end diameter is defined in terms of a supremum, this will give you the supremum of harmonic functions. So if you take the minus of this, then you get infimum of a family of harmonic functions on the unit disk. And then because the end diameter decreases to the logarithmic capacity, the same is going to be true for minus the log of the logarithmic capacity of the holomorphic motion. Okay, so what we get is that this function here minus the log of capacity of f lambda of A as a function of lambda, this is a pointwise infimum of a family of harmonic functions on the unit disk. And now if we normalize everything, then we get that the harmonic functions can actually be taken to be positive. And so we have positive harmonic functions. They always satisfy Harnack inequality. And from this Harnack inequality, it's easy to deduce the continuity of this function, continuity in terms of the parameter lambda. Okay. So this is sort of the idea how you show that the capacity of a holomorphic motion changes continuously according to the parameter. The precise details are not that important, but just keep in mind that we proved continuity by writing down the function that we're interested in, or in this case, minus the log of the function we're interested in, as an infimum of a family of harmonic functions. And then we were able to use Harnack inequality to get continuity. This idea is going to come back when we study dimension. Okay. Okay, so let's talk about dimension now. So the question that we've been interested in is the following. So you start with any set in the plane. So it doesn't have to be dynamical. It doesn't have to be a Julie set, just an arbitrary set. And you start with an arbitrary holomorphic motion. But what can we say about this function? So the variation of the dimension of the set A under a holomorphic motion. So what can we say about this function? So in the table, I mentioned that it is continuous and that in the case of packing dimension, we know the precise regularity and we have partial results for Hausdorff and Minkowski dimension. Okay, so here this notion of DIM denote any reasonable notion of dimension that you might want to study. What we studied are Hausdorff, packing, and Minkowski, but it could be other notions of dimension as well. Okay, so I have a few slides here just to recall the definitions of these dimensions. So I'll go a little bit quickly. So Hausdorff dimension is certainly very familiar. So we first define the Hess dimensional Hausdorff measure, where we try to minimize the sum of the diameters to the power s, where the sets are covers of A with diameter less than delta. Then we let the upper bound on the diameter delta go to 0. That gives us the S dimensional Hausdorff measure. And then the Hausdorff dimension is this critical value below which the Hausdorff measure is infinite and above which the Hausdorff measure is equal to 0. We also have the packing dimension, which is defined sort of similarly, but there are important distinctions. So our first difference is that we use packings instead of coverings, and we use packings by disks. So we look at the sum of the diameters to the power s, but we look at the sets to be disks, which are centered in the set A, and the diameter, again, should be less than delta, and then we take the limit as delta goes to 0, but in this case, we're doing a supremum instead of an infimum. So that gives us what we call the pre-packing measure. Unfortunately, it's not a measure itself, so we have to turn it into a measure by doing this trick where we minimize the sum of the pre-packing measure over all coverings of the set A. And if you do this, then you do get a true measure, and then you can define the packing dimension, again, as this critical number, where the packing measure goes from infinity to to 0. And then a Minkowski is defined differently. So it involves the smallest number of sets of diameter at most delta that you need to cover the set A, and then there is a lim sup. So here I'm using upper Minkowski, so I'm using the lim sup. In general, the limit need not exist, so you have to sort of choose if you want to use the lim inf or the lim sup. Okay. Okay, and oh yeah, I can also mention that. Sorry about that. Can you hear me? Hello? Raise
Yes,
your
we
hand.
can hear
Yes.
you.
Okay. Thank you. Sorry about that. My headset just turned off. What was I saying? Oh yeah, so we have these inequalities between those dimensions. So Hausdorff is always the smallest, Minkowski is the largest, and then Peking is in between. Okay. Okay, so now what I'd like to do is try to go back to this question, the variation of dimension. What can we say about this function as a function of lambda in the unit disk? So what kind of answer can we hope to obtain to this question? What kind of function could that be? Well, for this, we can go back to the bounds obtained by Astola on the distortion of dimension under quasi-conform mappings, cost of dimension at least. So here, this is the Astola inequality written in terms of the parameter little k. So this applies to any quasi-conform mapping, but now remember that if you have a quasi-conform mapping, then you can always embed it into a holomorphic motion. So this inequality that we have here can be restated in terms of an arbitrary holomorphic motion. And then for a holomorphic motion, the little k is the absolute value of lambda, so that's why we replaced little k by absolute value of lambda in those inequalities. So now we have these inequalities for an arbitrary holomorphic motion. And I write this in this way just to make the following point. So if you look at the function in the middle, 1 over the dimension minus 1/2, so that's always a positive, a non-negative function, a function of lambda. And then what you have on the right-hand side is 1 plus lambda over 1 minus lambda multiplied by the very same function that's in the middle, but when lambda is equal to 0. Lambda is equal to 0, f0 is just the identity. And then on the left-hand side, you have the same function at 0 multiplied by 1 minus lambda plus lambda. And so if that rings any bell, this is exactly Harnack inequality applied to a specific function, namely the function 1 over the dimension, and then normalized by subtracting minus 1/2. Okay? So the bottom line is if we can show that for any holomorphic motion and any set, the function that we have here, 1 over the dimension, is always satisfies Harnack inequality, then that gives another proof of the Astola inequalities. So that's the first observation. Another observation is if we want to study instead the variation of dimension of quasi-circles. So for quasi-circles, we have that the set A is the real line, so there's an additional symmetry in the set. And this additional symmetry, this was observed by Smirnov a while ago, results in some kind of improved Harnack inequality. So in this case, we hope to be able to use a better Harnack inequality. And then if we do this trick where we embed a quasi-conform mapping inside a holomorphic motion, there's a little calculation that needs to be done here. But if you have this improved Harnack inequality, and then you set the parameter lambda to be equal to little k, then you'll get that the lower bound will give you something like this, so a lower bound for 1 over the Hausdorff dimension. In other words, an upper bound for the Hausdorff dimension itself. And then if you do the calculation, the upper bound turns out to be exactly what you would expect to be from the work of Smirnov, this 1 plus k squared. Okay, so really all we have to do is try to show that this function here, 1 over the dimension, satisfies Harnack inequality. And in the case of the real line, maybe it satisfies a better type of Harnack inequality. If we can prove this, then we sort of recover these bounds of the distortion of dimension under quasi-conform mappings. And now what kind of functions satisfy Harnack inequality? Well, if you remember the discussion we did about logarithmic capacity, then we proved Harnack inequality by proving that it is the infimum of a family of positive harmonic functions. And those types of functions are important for our purposes, so we gave them a name. We call them inharmonic or infimum of harmonic functions. So that's the following definition. If you start with a positive function, then we call it inharmonic if it can be written as the infimum of some family of positive harmonic functions on unit disk. And these types of functions, they satisfy some degree of regularity, not much, but some. So they're always continuous, for example, which follows from the fact that they satisfy Mac inequality. And it's also not difficult to see that they're always super harmonics. They satisfy some kind of minimum principle, for example, in all of the properties of superharmonic function. Okay, so we have these inharmonic functions, infimum of harmonic functions on the unit disk. And now I can state our main result. So the first main result only applies to packing and Minkowski dimension. Mention Hausdorff in a few minutes. And it says the following, that if you start with any holomorphic motion, no assumption, any set, no assumption on the set either, then 1 over the dimension, and then you can subtract 1/2, sort of normalize everything, is always inharmonic. So it can always be written as the infimum of a family of positive harmonic function. So it sort of illustrates this first quote that we saw at the beginning of the talk, that you get a lot for free when you study holomorphic motions. So sort of if you want the ratio of the definitions that you need, or the ratio of what you can prove over the definitions that you need is very high. You can prove a lot of things just starting with very simple assumptions, and this is one example of a theorem that can be proved for arbitrary holomorphic motion, which is not obvious at all from the definition. And we do also have a converse to this theorem. Sort of technicality is that the converse only applies to packing dimension and Hausdorff dimension. It's not Minkowski this time. And it says basically that if you start with any inharmonic function, any function d whose reciprocal is inharmonic, then you can always realize that function as the variation of the dimension of some compact set under some holomorphic motion. And we can construct the set and the motion so that the Hausdorff dimension is always equal to the packing dimension in this case. So in particular, that gives a complete characterization for the case of packing dimension, because the previous theorem tells us that packing dimension, 1 over the dimension, is inharmonic. And then that converse tells us that any inharmonic function can be obtained from the variation of the packing dimension under some holomorphic function. Okay? So just circling back to the entry in the table, so that's why I wrote yes for packing dimension, because these two theorems combined give us a complete answer. And an interesting consequence of this is the following. So there's been a lot of work done on looking at the variation of Hausdorff dimension, for example, under holomorphic motions, if you consider some special collections of sets, like Julia sets of hyperbolic rational maps or limit sets of Fuchsian groups with special properties, and then trying to show that in this case, this function, dimension of f lambda of e, has a very nice degree of regularity. For example, it's real analytic in some cases, which is sort of one end of the spectrum. But then you can ask yourself, what about the other end of the spectrum? Can you construct motions of sets where the dimension is not regular at all? What kind of lack of regularity can you obtain? And as a consequence of our theorem, we are able to obtain examples where the dimension has essentially the same lack of regularity as an arbitrary concave function. So that's the following corollary. So if you start with any concave function, then you can realize it as the dimension of some holomorphic motion for some compact set. Well, not technically not the concave function that you realize, but 2 over 1 plus the concave function, just to make everything between 0 and 2. Okay. And this essentially follows from the fact that if you have a concave function, then it's actually inharmonic. You can write it down as the infima of affine linear functions. Yeah. Okay, so we have this corollary that applies to packing and Hausdorff. So there's sort of something missing in this description that I haven't mentioned, is what about Hausdorff dimension? So if we go back to the first theorem, it does not apply to Hausdorff dimension, unfortunately. We were not able to prove that the variation of Hausdorff dimension is inharmonic, or 1 over the Hausdorff dimension is inharmonic. So the best that we were able to prove is the following, not super satisfying result, but that's the best we have, where we show that maybe it's not inharmonic, but we can show that it is the supremum of a family of inharmonic function. It's like instead of proving something as a G delta, you prove it's like a G sigma delta or whatever. Like, yeah. So it's not exactly the same thing, but it's at least it's a partial answer. In general, the supremum of a family of inharmonic functions need not be inharmonic, so we still don't know whether this function is inharmonic or not. But at least if you have the supremum of a family of inharmonic, then this is enough to get the Harnack inequality, which is what we really need for the applications to the study of properties of quasi-conformal mappings. Okay? So as I mentioned, we still don't know. That's an open question. As far as I know, is the variation still is the variation actually inharmonic, not just a supremum of inharmonic functions. Okay? Okay, so I discussed this a little bit, but this approach using inharmonic function kind of provides a unified approach to several theorems about quasi-conformal mappings. And so, for example, we can use it to prove Hasteller's bounds, not just for Hausdorff dimension, but for all 3 dimensions, packing Hausdorff and Minkowski as well. We can also show Smirnov's 1 plus k square bound using these techniques and inharmonic function. So we can prove it for the Hausdorff dimension of quasi-circles, but also for the Minkowski dimension of quasi-circles. This was done by my student, Catherine, who's here at this workshop. So this is not a new result. This was known before, but that gives a new proof of this theorem. And then if you look at the paper, we also have, as another application, a new proof of another result of Pals and Smirnov on the distortion of dimension under quasi-symmetric mappings. And then if you look at the proofs, they're sort of elementary in the sense that we don't really need any hard analysis on quasi-conformal mappings. The properties of quasi-conformal mappings we use are essentially this weak quasi-symmetry property. So we don't need sublevel regularity, for example, or anything like that. Okay, and I have a couple of minutes left, I think, so maybe I can mention something quickly. So we've also been thinking about the variation of area under holomorphic motion. So I mentioned that area always varies continuously. This is easy to show, but can we describe what kind of function we get in this case? And we have a theorem, but it's sort of a technical partial answer. So basically, you need some technical assumption on the holomorphic motion. So you need the motion to be conformal outside of some compact set delta, and you need it to be normalized with the usual hydrodynamic normalization at infinity. And then if you consider a Borel set and you move the Borel set around, how does the area changes as the set goes under this holomorphic motion? Well, the answer is sort of depends on 2 cases. So if you know that basically those maps F lambda are conformal almost, or conformal on the set A, then you get that this function, the log of some constant divided by the area, will be inharmonic. And then in the other case, if the Beltrami coefficients are 0 almost everywhere outside of the set, then you get that the area itself is an nth harmonic function. So there's sort of these two cases that we haven't been able to combine together. But it is enough to get the optimal results of the distortion of area under quasi-conformal mappings. Basically, because if you have a quasi-conformal mapping, then you can write it down as a composition of two quasi-conformal mappings, one which is conformal on the set A, and the other one which is conformal outside, quasi-conformal outside of the set A. No, sorry, one that is conformal on A, and one that is conformal outside of the set A. And then if you use this decomposition, then you get the following inequality. So this was proved by Eremenko and Hamilton, the precise sharp estimate, and we were able to obtain a new proof of this using these nth harmonic functions in the previous theorem that I just showed. Okay. Okay, I think that's all I had to say today about nth harmonic functions. So thank you for your attention.